When the hot metal interacts with its environment, many of the reactions result in products that dissolve rapidly in the metal and diffuse away into its interior. Some of these processes have already been described, but now we shall focus our attention on the products of reactions that remain on the surface. Whether there is any tendency for a film to form or not depends on its stability, which can be quantified by its free energy of formation. A diagram for oxides showing this energy as a function of temperature was famously promoted by Ellingham and is shown in Figure 1.5. The extremely stable oxides are at the base, and those easily reduced back to their component metals are high on the graph. In reality, the kinetics of the formation of oxides and other compounds depends on the rate at which components can arrive and the rate at which they can be processed. Oxide films usually start as simple amorphous layers, such as Al-O on Al or MgO on Mg and Al-Mg alloys. Their amorphous structure probably derives from the amorphous melt on which they nucleate and grow. However, they quickly convert to crystalline products as they thicken, and later often develop into a bewildering complexity of different phases and structures. Many examples can be seen in the studies reviewed, showcasing how some films grow slowly while others develop quickly. Some are heterogeneous and complex in structure, being lumpy mixtures of different phases. The nature of the film on a liquid metal in a continuing equilibrium relationship with its environment needs to be appreciated. In such a situation, the melt will always be covered with the film. As a result, the melt will always have a protective layer, influencing its properties and reactions. This interaction not only affects the surface characteristics, but also impacts the overall behavior of the metal during processing. Understanding these dynamics provides insight into how films evolve and their implications for material properties. Researchers can manipulate these variables to control the outcome and improve material performance in various applications. The knowledge gained from studying oxide film formation is crucial for advancing technologies in metallurgy and materials science. Figure 1.5 presents a scientific illustration of the Ellingham diagram, showcasing the relationship between free energy formation of anides and temperature, reflecting complex interactions within metal surfaces in a foundry environment. As we delve deeper, the formation of oxide films results from moisture decomposition, while cranhitic films arise from hydrocarbon breakdown, enhancing the presence of hydrogen within the metal structure. Noble metals such as gold, platinum, and iridium stand out for their film-free surfaces, demonstrating an inherent stability noted in the Ellingham diagram due to their oxide reduction properties. Iron and steels exhibit a unique complexity, their behavior characterized by both solid and liquid films, as highlighted within the context of the intricate relationships shown in the Ellingham diagram. The examination of various casting alloys reveals differing surface characteristics, where the presence of films plays a crucial role in metal performance, further investigated by skilled technicians in a lab setting. Illustrating the underlying chemical processes, the reactions leading to oxide and cranhitic film formation can significantly alter metal properties, a focus of ongoing research within laboratory experiments. Educational resources showcasing the Ellingham diagram help students grasp critical concepts of free energy and its role in film formation, sparking interactive discussions during hands-on lab activities. Summarizing the significant impacts of surface films on metal properties, these infographics serve as valuable tools for scientists sharing their research at conferences, emphasizing the importance of understanding these phenomena. Capturing real-time interactions within a research facility, these experiments reveal how various environmental factors contribute to the dynamic formation of surface films on metal samples. Data visualization through bar graphs presents a clear comparison of metal susceptibility to film formation, guiding engineers as they analyze experimental outcomes and strive for improved material properties. Preparation for experiments is crucial, as technicians carefully clean metal samples, while interactive displays offer engaging simulations of the Ellingham diagram, enhancing understanding of film formation dynamics. The intricate dance of hydrogen within a molten copper alloy reveals how different concentrations interact to reach equilibrium, as seen in various environments where gas pressures shift. Observing the equilibrium process, scientists notice how high concentrations of hydrogen begin to dissipate, while lower concentrations absorb gas, ultimately balancing out in harmony. The researcher adjusts the gas pressure settings, witnessing firsthand the transition of hydrogen molecules as they shift from areas of high concentration to those of lower pressure, illustrating the dynamics of equilibrium. As bubbles form and burst in the molten copper, it becomes evident how vigorously gas interacts with the liquid, embodying the fundamental principles of gas-liquid equilibrium. The temperature of the molten copper plays a crucial role in gas solubility, as researchers study the fluctuations that affect how much hydrogen can be absorbed into the liquid. In this controlled environment, variations in temperature reveal striking differences in hydrogen absorption, as scientists meticulously record their findings to understand the complexities of gas behavior in liquid metals. As time progresses, the gradual shifts in hydrogen concentration become evident, illustrating how the system steadily approaches equilibrium while the liquid cools. Through advanced simulations, researchers explore the intricate molecular dance between hydrogen and copper, unveiling insights into the mechanics of gas absorption and dissolution. The contrast between hydrogen-saturated and neutral copper alloys reveals significant changes in texture, as microscopic examination uncovers how gas presence alters material properties. The phase diagram of the copper-hydrogen system provides a comprehensive overview of solubility conditions, guiding researchers in understanding the intricate relationship between temperature and gas absorption. As researchers meticulously adjust hydrogen pressures, the impacts on the melting point of copper alloys become apparent, showcasing the delicate balance between gas concentration and material behavior. The cooling process reveals fascinating solidification patterns in the copper alloy, as trapped gas pockets signify the intricate relationship between hydrogen absorption and material formation. This concept can be grasped by considering bubbles of gas which have been introduced into the liquid floating about. The presence of gas bubbles creates a complex dance of molecules at the surface, leading to intriguing reactions between the gas and the environment. Atoms of gas in solution migrate across the free surface of the bubbles, and in a microscopic view, a surge will be expected between the individual atoms of the liquid. It is clear that the equilibrium gas pressure of a melt applies to both external and internal environments. We have so far not touched on those processes that control the rate at which reactions can occur. Consider, for instance, the powerful reaction between the oxygen in dry air and liquid aluminum. The reaction is held in check by the surface oxide film, slowing further oxidation. A further example is the beneficial effect of water vapor in strengthening the oxide skin on the zinc alloy during hot dip galvanizing, producing a smooth layer free from imperfections. Without the water vapor, the growth of surface crystals disrupts the smoothness of the liquid zinc film. Water vapor is also known to stabilize the protective gamma alumina film on aluminum, reducing the rate of oxidation in moist atmospheres. His results reveal that the oxidation rate in moist air is generally lower than in dry air or pure oxygen. The kinetics of surface reactions can also be strongly influenced at the atomic scale by surface-active solutes that segregate preferentially to the surface. Only a monolayer of atoms of sulfur will slow the rate of transfer of nitrogen across the surface of liquid iron. Gases in solution in liquids travel most quickly when the liquid is moving, as they are simply carried by the liquid. However, in many situations of interest, the liquid is stationary, especially in the boundary layer at the surface of the liquid. The presence of a solid film on the surface will hold the surface stationary, and the effect of viscosity will cause this stationary zone to extend into the bulk liquid, impacting gas transport dynamics. As gases diffuse and interact with the surrounding liquid, bubbles start to burst at the surface, releasing trapped gases and illustrating the profound impact of gas transport on the overall system. The process of bubble formation is integral to understanding gas transport. As bubbles grow, they create pressure that eventually leads to their explosive release at the surface. In controlled environments, scientists monitor the behavior of gas bubbles in liquids, seeking to understand the intricate dynamics that govern their formation and release. Various factors affect gas solubility in liquids, including temperature and pressure, which play crucial roles in the dynamics of how bubbles form and dissolve. Understanding gas solubility reveals significant variations among different gases, especially as temperature changes, affecting how they interact within liquids. The effect of temperature is evident as bubbles rise through the liquid, demonstrating how heat influences gas solubility and the behavior of dissolved gases. As gas bubbles rise and burst at the surface, they create dynamic splashes, illustrating the powerful forces at play when gases are released from liquids. The coalescence of gas bubbles illustrates fundamental molecular interactions affecting their size and stability, while demonstrating the intricate processes involved in gas exchange. In highly agitated liquids, the rapid formation and collapse of bubbles create an energetic atmosphere, emphasizing the complex interplay of forces acting on each bubble. As bubbles rise through the liquid, their varying sizes create a stunning visual effect, reflecting the intricate gas dynamics at work beneath the surface. In slow motion, the bursting of gas bubbles reveals the intricate beauty of droplets scattering, showcasing the dynamic interactions between gases and liquids. Researchers closely observe gas bubbling through liquid, meticulously measuring factors like gas concentration and temperature to understand the underlying chemical processes. The concept of saturation becomes evident as illustrations depict the point where a liquid can no longer absorb additional gas, showcasing the equilibrium between gas and liquid. Laboratory experiments demonstrate how different gases react upon introduction to a liquid, creating bubbles in unique patterns based on their physical properties. As heat increases, gas bubbles form vigorously at the surface, demonstrating the relationship between temperature and the rate of gas diffusion in liquids. The boiling of a liquid creates aggressive bubble formation, highlighting the energetic interactions between heat and the liberation of gases. In a large boiling pot, bubbles rise and burst energetically at the surface, illustrating the phase transition from liquid to gas during the boiling process. The layering of bubbles in the liquid reveals variations in size and formation rates, driven by underlying factors like temperature and pressure. In a time-lapse sequence, the rise of bubbles is captured, highlighting their interactions and merging dynamics as they make their way to the surface. The transition of gas molecules from a liquid into the atmosphere is beautifully depicted, showcasing the intricate process of gas release and diffusion. Bubbles rising through a colorful liquid create captivating visual effects, emphasizing the dynamic nature of gas interactions within different environments. Gas bubbles forming on the walls of a container highlight the role of surface tension, while energy changes in gas dissolution illustrate the complexities of molecular interactions. It is self-evident that it has succeeded to escape the attention of most of the casting community for the last several thousand years. The techniques to avoid entrainment during the production of cast material represent an engineering challenge that occupies much of the second volume of this book. When melting and casting metals, temperatures are often sufficiently high that some alloy components will be evaporating all the time. The evaporation of elements from melts can be severe and has consequences of which it is useful to be aware. Although examples will occur repeatedly throughout the book, a number of instances are gathered here to illustrate how common the effect is. Zinc similarly evaporates from QZN alloys and can oxidize, creating the familiar zinc flare. The wind of vapor blowing away from the melt seems responsible for the lack of gas porosity problems in the zinc-containing brasses. This interesting and useful phenomenon is dealt with in more detail in section 6.4. An increase in the pressure of vapor of some of the more volatile elements as temperature increases. Data from these observations reveal significant insights into the behavior of sodium, zinc, and other elements in heated conditions. The implications of these findings are critical for understanding the complexities involved in metal casting and processing. Understanding these vaporization effects allows for more precise control over the casting processes and improves overall material quality. This knowledge not only aids in the development of better alloys, but also enhances safety protocols in industrial settings. The careful management of temperatures and environmental conditions is crucial to prevent unwanted reactions and ensure successful outcomes in metal casting. Each stage in the casting process is interconnected, relying on precise measurements to achieve optimal results. Continuous research and innovation are essential to advance the understanding of materials science and improve casting techniques. These experiments are pivotal for refining our techniques and enhancing the performance of alloy materials in various applications. The collective effort of researchers leads to breakthroughs that push the boundaries of what's possible in metal casting and material engineering. Depending on the composition of the alloy and its temperature, various behaviors can be observed in the casting process, presenting challenges and intricacies that metallurgists must navigate. Liquid silver behaves similarly to copper as it dissolves oxygen, leading to the formation of silver oxide that tarnishes, a fact that every jeweler is well aware of. At higher temperatures, the free energy of formation of silver oxide becomes positive, indicating instability. Thus, it is not expected to exist in such conditions except during brief non-equilibrium states. The oxides created during the casting of alloys often become permanent features, significantly affecting the final product depending on where they settle in or on the cast materials. Various important alloys exist that, despite their main components being harmless, create troublesome films in practice because they include just enough highly reactive metals. The AMG alloy family, known for their challenges in casting, actually possesses admirable ductility and toughness when executed properly, making them preferred in industries requiring decorative finishes. Aluminum bronze, which can contain up to 10% aluminum, requires much higher casting temperatures than aluminum alloys due to the thick, tenacious film of Al2O3 it produces. Ductile irons are significantly more difficult to cast free from oxides and other defects compared to gray cast iron, primarily due to the magnesium concentration added to enhance graphite structure. In some cases, the chemistry of the surface film can be manipulated to convert it from a solid to a liquid, reducing the risks associated with entrainment events during the casting process. The elimination of entrainment defects in cast products cannot be achieved by stopping the formation of films. Rather, the problem can be resolved through improved filling system designs. Implementing an improved filling system design can dramatically enhance casting quality, providing a straightforward solution to the complex issues of entrainment defects in materials. As we progress through this work, we will explore how various innovations in casting technology can significantly reduce defects and enhance the overall quality of metal products. Throughout this investigation, we shall uncover the relationships between alloy compositions and their behaviors during casting, revealing key insights for metallurgists and engineers alike. By examining the principles outlined in educational materials, future metallurgists will gain a deeper understanding of how alloy compositions influence casting processes and outcomes. The impact of temperature on alloy behavior is crucial, as variations can lead to significant changes in mechanical properties and the formation of defects in the final product. Microscopic examination of cast alloys reveals critical insights into their properties, enabling engineers to devise effective strategies for overcoming common casting challenges. Collaborative research efforts play a vital role in advancing our understanding of alloy behavior, paving the way for innovative applications and improvements in casting technologies. Precision machining of cast alloys is essential, as it allows for the creation of complex components that meet stringent industry standards and customer requirements. Quality control is paramount in the casting industry, as inspectors meticulously assess each component to uphold safety and performance standards. The foundry environment is alive with activity, as skilled workers manage numerous processes simultaneously to ensure efficient and effective metal casting. Real-time monitoring systems are revolutionizing the casting industry, allowing for precise control over temperature and composition to minimize defects and enhance product quality. Evaluating the mechanical properties of cast alloys through rigorous testing is essential for ensuring they meet the demands of their intended applications. Innovation is at the heart of metallurgy, as teams collaborate to explore new methods and materials that can significantly improve casting outcomes. The integration of automation and advanced data analysis in casting facilities serves to enhance production efficiency while ensuring high-quality standards are consistently met. Educational workshops for future metallurgists provide invaluable hands-on experience, promoting a deep understanding of the complexities involved in alloy casting. Preparing casting molds with meticulous accuracy is crucial, as even minor discrepancies can lead to significant defects in the final product. The finishing touches applied to cast metal pieces are essential for achieving a high-quality appearance and performance, ensuring they meet customer expectations. Utilizing advanced analytical techniques like XRF allows researchers to accurately assess alloy compositions, which is critical for maintaining quality and performance in casting processes. Collaboration in a dynamic workshop environment fosters innovation, as engineers focus on various aspects of alloy casting to streamline processes and enhance product quality. Conducting fatigue tests on cast alloys allows researchers to simulate real-world conditions, ensuring materials perform reliably under stress. Thermal cycling tests provide valuable insights into the behavior of alloys under fluctuating temperatures, helping engineers anticipate performance issues in practical applications. Hands-on learning experiences in classrooms empower students to grasp complex concepts of alloy casting, bridging the gap between theory and practical application. When melting and holding magnesium alloys in a low-pressure casting machine, it is essential to suppress the evolution of vapor by the presence of some air or other actively protective gas or flux above the melt. The experimental use of an inert gas, argon, above the melt to avoid oxidation led to the atmosphere becoming high in magnesium vapor, such that when the unfortunate operator opened the door to charge more ingots, admitting air, he was killed in the explosion. When vaporization is properly suppressed, the use of magnesium alloys in low-pressure casting machines is perfectly safe. In the production of ductile iron, magnesium is actually above its boiling point when added to cast iron. The addition reaction is therefore so energetic that the boiling action requires special techniques, often involving special reactor vessels to prevent the melt erupting out of the container. Alloys of copper and iron that contain lead are a particular problem because of the toxicity of lead. Thus, leaded copper alloys and leaded free-cutting steel are now being phased out. Manganese vapor from manganese steels similarly condenses in the molding sand and is thought to be responsible for the enhanced wetting and penetration of molds by manganese steels. Evaporation is a particular problem from alloys melted in vacuum. The charge makeup has to allow for the losses by evaporation. Furthermore, the condensation of the metal vapors on the cold walls of the vacuum chamber usually ignites when the chamber is open to the air. The fine black metallic dust then burns with a flame that licks its way around the chamber walls. If not burned on each occasion, the dust can accumulate to a thickness that might become dangerous. Even when the dust is oxidized, it is black, dirty, and can be a health hazard. Thus, vacuum melting and casting requires special personal care. Melting and casting in an inert gas such as argon greatly reduces the rate of evaporation and consequently reduces these problems. Inert gas usage in the casting process not only enhances safety, but also improves the overall quality of the finished products. The careful management of gaseous environments during the casting process leads to improved mechanical properties and surface quality in the final products. These advancements in casting technology reflect the industry's commitment to safety and quality in metal production. As the industry evolves, continuous research and development are essential to further enhance the melting and casting processes. Training and knowledge sharing among workers is crucial to maintaining high safety standards and fostering innovation in metal casting. The combination of cutting-edge technology and rigorous safety measures ensures that the foundry remains a safe environment for all its employees. Precise control over the casting environment is essential for achieving optimal results and preventing accidents in the foundry. Success in the foundry stems from the collective effort of skilled workers committed to excellence and safety in every stage of the casting process. Recognition of achievements in safety and innovation keeps the team motivated and focused on continuous improvement within the foundry. Regular workshops and training sessions empower employees to stay abreast of the latest practices and technologies in the metal casting industry. Discussions about the diffusion of various elements within metals like aluminum, copper, and iron reveal fascinating insights into atomic behavior. Hydrogen stands out as an interstitial element, remarkable for its tiny size, allowing it to infiltrate iron where carbon, nitrogen, and oxygen also exhibit similar, albeit slower, behaviors. In aluminum, common alloying elements like magnesium, zinc, and copper act as substitutional solutes, forming structured groups that play crucial roles in material properties. The melting behavior of copper and iron showcases these interactions, revealing how substitutional elements define their characteristics during phase transitions. Oxygen takes on an intermediate role within the copper lattice, distinctly altering its behavior compared to other elements. Meanwhile, sulfur and phosphorus in iron exhibit curious intermediate behaviors, a phenomenon that hasn't been widely recognized yet intriguing in its complexity. The rate of diffusion varies significantly among the different forms of iron, notably faster in the open body-centered cubic lattice than in the more densely packed face-centered cubic lattice. In the liquid phase, diffusion accelerates even further, highlighting how the rates of various elements behave differently when transitioning from solid to liquid. Equation 1.5 serves as a fundamental tool for understanding the relative rates of diffusion among elements, whether in solid or liquid forms. Throughout the exploration of this book, these diffusion rates are frequently referenced in relation to diverse phenomena, revealing insights into materials science and metal behavior. In a cutting-edge research laboratory, scientists delve into the intricate processes of metal diffusion, meticulously examining various samples and utilizing advanced equipment. An encompassing infographic captures the essential findings on diffusion rates, illustrating the pivotal roles played by interstitial and substitutional elements in these complex phenomena. Microscopic images reveal the intricate crystal structures of aluminum, copper, and iron, each possessing distinct lattice arrangements that affect their diffusion behaviors. An educational poster outlines a timeline of key discoveries in the realm of metal diffusion, highlighting pivotal milestones and the contributions of groundbreaking researchers. Figure 1.3 illustrates the growth of oxide on 99.9% aluminum at 900 degrees Celsius in a flow of oxygen, dry air, and moist air, with important implications for the behavior of solutes within liquids and solids. In this scene, we delve into how diffusion operates within various states of matter, highlighting that while liquids can facilitate rapid movement through stirring, solids rely solely on atomic jumping for diffusion. Here we explore the dynamics of diffusion within the partially solidified zone of a casting, where the slow drift of liquid allows for the migration of solutes through gradual diffusion. As we examine the diffusion equation, it serves as a fundamental tool for estimating the distances involved in reactions, bridging theoretical concepts with practical applications. In this segment, we identify the two broad classes of diffusion processes: interstitial diffusion, characterized by the swift movement of small atoms, and substitutional diffusion, which involves a more complex exchange of atoms within a solid structure. This visual comparison highlights interstitial diffusion as a relatively rapid process due to small atoms easily slipping through larger atomic spaces, while substitutional diffusion is depicted as more challenging, requiring careful coordination amongst similar-sized atoms. In this scene, we focus on the intricate arrangement of atoms within a crystal lattice, emphasizing the critical roles of both interstitial and substitutional diffusion processes in material behavior. This animation illustrates the dynamic process of substitutional diffusion, where atoms energetically seek out gaps to exchange positions, showcasing the fundamental nature of atomic interactions in solids. We now analyze a detailed graph that presents the diffusion coefficients of different elements, allowing us to understand how these properties influence the rates of interstitial and substitutional diffusion across materials. In this segment, we explore the real-world implications of diffusion processes, highlighting their significance in industries like alloy manufacturing and metal treatment, where atomic movement critically influences material properties.